So now we're up to limits number 3, my final exploration that I wrote out about limits and the concept behind limits. And we're going to get into it, but before we get into it, I want to talk about the man behind the curtain. Because I'm going to talk a lot in this class about the man behind the curtain. And of course, this is a reference to The Wizard of Oz. So in The Wizard of Oz, Dorothy and her friends go and see the wizard, and it's this big flashy bunch of fire and loud voice and looks very flashy. All right, but then Toto pulls back the curtain and there's a guy back there and he's just pulling all the levers. All right, a lot of what we do in calculus is going to be the flashy wizard stuff. So for example, when I told you in one of our earlier explorations that you were going to be able to look at y of t equals 120,000 minus 1.17 t cubed, and somebody's going to tell you this is the position of a probe as it descends to Mars, and you're going to look at that, and in less than a quarter of a minute, you'll be able to look at that and say, you know what, the velocity of that probe is a negative 3.54 t squared. And you know what else? The acceleration of that probe is, let's see, what's 2 times 3.54? It's going to be 7.08, right? Negative 7.08 t, all right? That's the flashy wizard. That's what you're going to learn to do. That's sort of the main stuff that you need to be a good engineer, physicist, economist, doctor, whatever you want to be able to be, design prosthetics, whatever. All right, design robots. You need to be able to do that stuff. So this is the flashy thing that you can do, and how am I doing that, and how will you be able to do that in less than a quarter of a minute? So that's the flashy in front of the curtain stuff. So behind the curtain, there's somebody pulling all the levers making this happen. That somebody is named Delta and Epsilon. At least in this case, when we're talking about limits, the guy behind the curtain pulling the levers is Delta and Epsilon. So we want to be able to understand stuff like that, and it's to a certain degree, your conceptual understanding is going to be necessary for tests and AP exams, but really only to the level of our limits number 1, where you had to do a bunch of average rates of change, and then you had to simplify and reduce, and then understand the difference between when it's reduced and when it's not reduced, be able to understand what value something is approaching as something else approaches 0, understand instantaneous rate of change. Those are things that you have to be able to do to be successful in this class, to be a successful engineer, or physicist, or whatever it is that you're interested in doing. So, but to understand, to be able to do those things without understanding what's going behind the curtains is a little shallow. Now, I don't want to, you can go on about Epsilon and Delta for weeks. I could easily do that. So another story that comes into play is Alice in Wonderland. Because Epsilon and Delta, in addition to being the wizard behind the curtain that make things happen, they're also a rabbit hole. So you can go down that rabbit hole, and you can go down there. There's lots of doors. There's rooms that make you bigger, rooms that make you smaller. It's very fascinating, and there's a lot going on back there. We're not going down the rabbit hole, but we are going to peek behind the curtain. So those are my metaphors about how calculus is conceptually immensely dense and deep. So we got to hit the balance between how deep am I going to go with this stuff? What do I actually have to be able to do on a test? So limits number 3 is going to go pretty far past anything that you have to do on a test for me or for the AP exam or anything. However, it's going to be really good for you to follow through this, get as good, as solid as a conceptual understanding as you can, so that when you go to UConn and you take your Calc 3 and somebody asks you, what is a limit really, and they say, have you ever seen this before? You can say, oh yeah, I've seen that. And it has something to do with if the x is close enough to its target value, then the f of x is going to be close enough to its target value, and the epsilon and delta are used to define what we mean by close enough, and they are numbers that are positive, but they are sort of in some sense the smallest positive number. All right, this is the engine of limits. So you want to sort of have seen that. However, what I'm saying is you're never going to see epsilon and delta on a test. However, I want to share with you this conceptual background, and after we're done with limits number 3, I'm very rarely going to ever mention epsilon and delta again. However, you got to know they're always back there behind the curtain. Okay, so that's a little bit of metaphorical imagery before we get into limits number 3, and also a caution to, as usual, I want you to do this as much as possible on your own. I spent a lot of time really writing out very carefully every step to do. Try to read that, try to be able to do it, and then once you've made your best effort at all of it, and by the way, probably the most mysterious thing is going to be part 2 here, and we're going to talk a lot about part 2. So if you have trouble with part 2, that's okay, but really try to get part 1 and part 3, and then we'll go over this. I'll talk about all the things that we can pull out of this, and then I will feel confident that you have a really solid conceptual understanding of what a limit really is, and then we'll get into the meaty AP exam-y stuff of basically what you want to do with a limit is be able to look at this. And you want to be able to say the limit as x approaches 2 of f of x is 3. All right, that's what you need to be able to do. That's where we're going to go after this. But first, one last dive behind the curtain. Here we go with our next video.